Welcome to our aerosol process in deep convection discovery to parameterization breakout session that straddles the aerosol processes and cloud processes working group. Juven Fan, Chris Kappa, and Jim Smith are my co-conveners, and I am Dubey from Los Alamos. Let me get started by sharing just my screen. Okay, so great. Just to recap what was said yesterday, ARM and ASR data has focused on and made progress in shallow convection. Deep convection is much more challenging and is becoming a focus of recent and future ARM campaigns. And so here I just show a cartoon, my simplistic view of literature as a data guy. And you can see starting with the early work, and this is about a 16-year history, from the early work by Andy Andrea that showed that smoke suppresses rain and invigorates storms, to the IPCC AR5 highlight, where it does show that the deep, the physics and the microphysics and the chemistry of deep convection. It highlighted that. It moved on to more of a satellite view. I'm just highlighting a paper here where cloud and Calypso data was used to basically highlight different types of aerosols with different microphysical properties, with different impacts on deep convection. And more recently, with work that came out of Go Amazon, led by Jinan, that showed that convective invigoration is possible. And as we heard yesterday, we have this eagles and scream activity from the E3SM models. It's very timely for EEST for us to engage. And I'm really glad that eagles and scream are taken off, and some of us should be participating with that. And as you know, recently there have been fires, but also PyroCbs that have injected smoke into the lower stratosphere and upper troposphere. So the scale of the problem and importance is becoming there. And then we're moving on to cacti and tracer, in 2022. So it's a kind of my conceptualized timeline, and I will now hand it over to Sue to basically share the screen and get started.
All right, am I good to go, Dubey? Everything's good? You can see the screen?
Drive, please.
Excellent. All right, well, good morning, everyone, and thanks very much for the invitation to talk here today. And before I get going, I'd like to acknowledge my co-authors on this work. And so my plan today is to first present the results from a recent model intercomparison project, or MIP, which is actually the first of its kind that is being performed to evaluate the impact of aerosols on deep convective cloud properties. And the results of this MIP actually played a critical role in advocating for the Tracer Field campaign. And I know that some of you have seen some of the MIP results in some of the recent specialty meetings. However, I think given the focus of this breakout group and the upcoming Tracer campaign, I really felt it was valuable to present a summary of them again. And after that, I'll present an approach we've been developing and following in evaluating MIP models. So there are many aspects that may modulate or determine aerosol impacts on deep convective clouds. These include cloud environments and cloud types, as shown by Hein et al. In 2008. The storm in this, the stage in the storm life cycle, as we showed in 2006. And then whether you're examining isolated clouds or integrated cloud scenes, as shown by a number of large domain modeling studies. And then finally, differences in modeling frameworks as well. And it's actually these differences arising from the use of different modeling frameworks that we focus on here first today. And so the Aerosol Cloud Precipitation and Climate, or ACPC initiative, conducted the first model intercomparison project, or MIP, of aerosols on deep convection. And as I just said, the results of this MIP actually played a significant role in advocating for ASR's Tracer Field campaign. And so 7 state-of-the-art CRMs with varying aerosol and microphysical parameterizations were used to simulate the same case study of isolated deep convective clouds over Houston in Texas under varying aerosol concentrations. And we used various observations from this case study day to initialize and evaluate the models. And so the fundamental goal of the MIP was to determine really the range in convective cloud responses to changes in aerosol loading across the suite of state-of-the-art CRMs. And while we kept the experimental setup as close as possible for all of the MIP models, we fully recognize that there are many other aspects and parameterizations that will vary. However, as our goal was really to assess the range and responses of current state-of-the-art CRMs to aerosol loading, this is in keeping with our goal and in fact in keeping with the goals of MIPS more generally. And so the teams and the models involved are shown here in this table. And as you can see, there was a wide range of models, as well as a lot of international participation. Okay, so I'm going to jump straight into some results in. This animation shows the accumulated precipitation on the finest model grid, which grid spacing of 500 meters for the region in and around Houston, as well as along the Texas coastline for all 7 models involved in the MIP, as well as the stage 4 observations shown here in the bottom right. And as you can see, all of the models did indeed produce scattered convection. However, there's a wide range in the aerial coverage and the amounts of precipitation produced. And we can look at this then a little more quantitatively. This is a time series of accumulated precipitation. The different colors are different models in the MIP. The solid lines represent low CCN conditions, the dashed line high CCN conditions, and then the black line here, once again, is the stage 4 observations. And so first you can see by comparing the different colors that the precipitation differences vary more as a function of the model framework used than due to aerosol impacts. Secondly, most of the models, with the exception of 2, actually underestimate the 12-hour accumulated precipitation by more than 40%. And then finally, by comparing the solid and dashed lines of the same color, you can see that all of the models actually show a decrease in accumulated precipitation, bless you, with enhanced aerosol loading, with the exception of 1 towards the end. So quite a range in the precipitation responses. Now, while I don't have time to show all the figures associated with these results, we do actually see a number of common results. So with increased aerosol loading, all of the models actually show an increase in cloud mass and number concentrations, a decrease in rain mass and number concentrations in the warm phase regions, an increase in rain diameters, and then as well as an increase in average and/or ice mass. However, as with the accumulated precipitation, there is a wide range of and/or ice produced. All right, let's turn our attention to cold pools now, and what's shown here are frequency distributions of surface temperature perturbations. And as you can see from this figure, about half of the models show warmer, weaker cold pools with enhanced aerosol loading, while the other half shows stronger cold pools. And this is in spite of the fact that most of the models have weaker downdrafts and larger mean rain diameters, which will impact cold pool intensity. And these differences then point to differences in the treatment of the sedimentation processes, as well as surface parameterizations. Finally, then, what about the updraft dynamics? So shown here on the left is the mean convective column vertical velocity for clean and polluted experiments. And then on the right here is the percentage difference between the high and low aerosol cases. And if we look at differences in the vertical velocities as a result of aerosol loading, we see 3 specific trends. Firstly, in the lower warm phase regions of the cloud, all of the models do indeed have strong updrafts in the high CCN simulations compared with their cleaner counterparts. We did examine the vertical velocity tendency equation, and it's clear that this occurs through the thermal buoyancy term as a result of enhanced condensation onto more numerous smaller cloud droplets. Then in the mid-levels, there's actually a weakening in this aerosol-induced response in the updraft velocities. And this is due to the fact that much of the vapor is actually utilized in the lower regions of the clouds, and the air is therefore drier in this region. And then finally, above 7 kilometers, as we move into the cold phase regions of the clouds, there's actually quite a spread in the updraft response to increased aerosol loading. And when looking at the vertical velocity tendency equation, this demonstrates that the buoyancy term alone actually cannot explain these trends, and that the result actually appears to be strongly or closely linked to the vertical perturbation pressure gradient. Okay, so just to summarize the results then found from this MIP then, we looked at 7 state-of-the-art CRMs simulating the same case study. We set them up as closely as possible. All of the models produce scattered convection in and around Houston, and there are a number of encouraging similarities. So we see with enhanced aerosol loading, most of the models show decreased accumulated precipitation, increased cloud mass and number concentrations, decreased rain mass and number concentrations, increased raindrop diameters, and increased total and/or ice mass. Also, the bulk of the models show weaker downdraft velocities, as well as increased updraft velocities in the warm phase region and longer-lived or greater ample extents. However, there are also a number of important differences. Firstly, precipitation varies more as a function of model physics than aerosol impacts. There's a wide range in annual ice mass amounts, which has cloud radiator forcing implications. There's a mixed response in the mixed through ice phase regions of the clouds in terms of the updraft velocities. And then there's also a mixed response in the cold pools, with half of the cold pools showing weaker and the other half of the cold pools, half of the models showing weaker and the other half of the models showing stronger cold pools, in spite of the fact that all of the models show weaker downdrafts and most have larger raindrop diameters. And so, of course, this then has important implications for storm longevity, convective initiation, and so on. And so the question then that we have to ask ourselves now is, how do we move forwards then in resolving these important differences? And perhaps just as importantly, evaluating the similarities, because just because the models produce a similar response doesn't necessarily mean that the response is correct. And so I've been working with Mariko Ui and Steve Salibi, Pavlos Kolios, and others to determine two questions really. The first is, what is the most appropriate way to evaluate these MIP results? And then the second is, what ways can the models be used to assist in field campaign observational strategies and or explain some of the processes observed. And so our aim then has been to assess really microphysical process rates as a function of cloud life cycle, cloud type, the thermodynamic environment, aerosol loading, and then the model framework. And this goal therefore touches on all of the uncertainties that I started out discussing today when it comes to assessing aerosol impacts on deep convective clouds. So this figure here is really an example of what we would like to produce for all of the MIP models, as well as for a number of the upcoming tracer field campaign case studies. In essence, it shows a time series of the relative processes, which you can see indicated here as a function of height for the composited deep convective clouds simulated by one of the models, WRF along the top, another of the models, RAMS along the bottom, for different aerosol concentrations. So low on the left, high on the right. And the figure then is centered on the time period of maximum latent heat release within the simulated storm systems. And then the cells comprising the composite are tracked throughout their lifetimes using towback. And without delving into any of the details, it's clear from this figure, for example, that melting, shown here in orange, is a more important process to RAMS than it is to WRF in clean conditions. And if you look in this direction, that melting becomes less significant a contributor to RAMS in the high CCM conditions. And so we've decided to make use of the following approach then. First, we're using instrument simulations to ensure apples-to-apples comparisons, as well as assessing appropriate field campaign strategies through RC approaches. Secondly, we're tracking, in essence, large numbers of individual clouds under multiple thermodynamic and aerosol environments in both observational and modeling data sets. And then finally, we're going to assess both the isolated and regional responses of aerosol loading in terms of convection, as both are important to model parameterizations across the scales. And so in essence, this graphically summarizes what we are doing. This example shows our basic steps with total hydrometering mixing ratios produced in this case by RAMS on the left, the conversion then to radar reflectivity using the simulator developed by Mariko in the middle here, and then finally on the right, a wide range of track cells detected using the towback tracking approach. And then once we have tracked the convective cells for clean and polluted conditions, we can then use these data, of course, to analyze storm characteristics and process rates, as well as to determine how closely different radar observations relate to simulated microphysical processes. And so what is shown here is, again, these are timed, in essence, it's a time series that's normalized by the life cycle, but it's a time series of the maximum differential reflectivity in the top here, and then the maximum mass weighted mean rain diameter in the bottom, for clean on the left and polluted conditions on the right. This is for one model, the RAMS model. And in essence, these are frequency accounts. And then in order to generate their composites, given that we wanted to composite all the different convective cells, we normalized by the convective cell lifetime. And so it's clear from this plot on the top that ZDR is actually greater in the polluted cases, and that this corresponds quite nicely with the larger rain mean diameters produced by the model. And so in essence, these results then indicate first that the model produces larger raindrop diameters in more polluted conditions. And then secondly, that ZDR is a relatively good representation of the raindrop size distribution. And hence it'll be, really useful to have such results in tracer. And then secondly, just another example of examining KDP in the ice phase shows that KDP is slightly larger in the polluted environments compared with the clean environments, which is in keeping with the model's prediction of larger mean hail diameters in polluted environments. And once again, KDP therefore appears to be useful in terms of indicating information about ice size distribution and amounts. And then it appears that these large hailstones are supported by some of these stronger updrafts observed in the polluted case. And so finally then, this is my last slide, really just to close the loop. In order to address MIP differences and uncertainties, it seems then to make sense to do the following: to select appropriate clean and polluted case studies from the Tracer Field campaign, to use instrument simulators, translate the model output to radar observations as observed by radars in the field, and evaluate all of the models of the MIP, and then track the simulated and observed cells using TOBAC, build composites to compare the observations with the models, assess then the predominant processes and how they're impacted by aerosol loading, and then upscale these results in essence to evaluate regional responses. And so finally, for more detailed description of all of these activities, would really encourage you to take a look at the posters from Mariko and Steve, as well as their combined talk, all of which are actually occurring tomorrow. And so with that, I'll thank you for your attention.
Hello, everyone. It's very nice to be here. My name is Pengfei. I was a postdoc in NOAA when I doing this convection research, writing a GRL paper. I'm an aerosol modeler. I'm interested in stratosphere aerosols and the troposphere stratosphere exchange. When we analyzing the aerosol budget in upper troposphere, we found this problem in CESM, and we fix it. So that's the paper. So the model tool we're using is called COMMA. So CESM COMMA is a sectional aerosol model, and the data we're using is primary is NASA ATOM data. And for this talk, CSR and the black carbon are showing in our GRL paper, and also there's also dust from Carl's paper is coming. So here's a story that in climate model, we have time step like 30 minutes, and aerosols can be activated at the cloud base. And that's the problem that if you don't have secondary activation, then in one time step, the aerosols can be transported to upper troposphere just in one time step. So those aerosols cannot be wet removed efficiently. So they will be there. So that's apparently wrong. So we fix it by introducing the subgrid scale secondary activation, which means above the cloud base, you have air in trend with new aerosols, and those aerosols can be activated to cloud and be removed in cloud. So here's the result. The vertical axis is altitude or pressure. The horizontal axis is a sea salt mass concentration. Observations are in red and green, so they drop from surface to upper troposphere by orders of magnitude. And if we don't have secondary activation, the climate models were showing no gradient, no vertical gradient. That's apparently wrong. So that's if we introduce secondary activation, the model agrees the observation well. So that's for sea salt and also black carbon. I didn't show here. This is for dust, and this paper is in revision now. And the dust showing a similar story that you have to have secondary activation to remove dust. The left panel, the solid lines are observations, and the dashed lines are model runs. So I don't have too much time on that. So the long dashed are a default model without activation, and the other dash lines are revised scheme. So agree with observation better. So not only in in the remote region, NASA ATOM measured the remote ocean vertical profiles. We also found in Asian summer monsoon region and also in Amazon rainforest, we found a similar story that the secondary activation dominates the vertical determines the vertical profiles of aerosols. What's the impact of that? So this is a simulated primary aerosols, including sea sawdust and primary organic aerosols and black carbon. The vertical profiles, top is with secondary activation, and the bottom is a default CESM model without secondary activation. So it's totally different. The color is in log scale. So in the upper troposphere, there's basically no primary aerosols. They all mostly secondary aerosols like sulfate, ammonium, and nitrate. So here a summary that NASA ATOM observations show the sea-salt black carbon and dust concentration decreased by orders of magnitude, and we need to have secondary activation in the model to reproduce the observations. So take-home message is we need to consider that, and also the removal rate is still parameterized with limited constraints. Thank you.
Let me go ahead, start with Amazon. So Amazon has a very unique environment for aerosol cloud interactions. It's warm and humid. And the Go Amazon Field campaign was designed to disentangle aerosol impacts from the impacts of meteorological conditions. So we have this Dewey arm sites at T3, which is downwind of the Monash City. And the day-to-day weather can be very similar, but aerosol can vary. So we have those unique observational data sets. For example, the convective intensity for the in-cloud convective intensity and the aerosol set distribution can measure down to 10 nanometer. So over this region, we see that ultrafine aerosol particles, which is those smaller than 50 nanometer, they are very high in concentrations. And the larger particles, which is larger than 50 nanometer, they are pretty low. This is make UIP effect can be very significant. So under this setup, we carefully selected the 17 locally occurring deep convective storms from the 2014 wet season. And we found that there's a good correlation, very significant correlation of the updraft velocity with the increase of aerosol from the low aerosol group to the high aerosol group. And this is very significant. You can see this is the mean body velocity for top 10 percentile for each convective core. And it's from 3 to 10. And the same as the red reflectivity. So with models, without include those smaller particles, which is when you exclude these small particles, we don't see a clear relationship. We also did the correlation with the other meteorological variables and didn't find any clear relationship. With models, with a Wolf spectrum beam at the 0.5 kilometer resolution, we simulated a very large increase. Those increase we never see actually in other places, which we did in many other locations. And this is pretty unique, our Amazon. And we see very significant increase also in the rain rate. This is the area, black area shows the increase by the UOP from Monash Canoe. And this is because the large activation of those smaller particles inside the clouds enhance condensation, brings down the supersaturation dramatically. That's invigorate convection. So this is so-called world phase or one phase immigration has been discussed in many previous studies, but over this region, it's particularly significant because of the large number of ultrafan and the very humid condition. And this effect does not suppress wall rain. This is a significant feature compared to the CCN effect, which is the larger aerosol particle effect, and allowing the cold phase invigoration. And then this effect usually is it's more significant as we see the enhanced latent heat is usually larger, and the heat is at the lower middle level. So goes to Houston, we found a very similar mechanism, but the magnitude are smaller. This is our recent study, and we did this case for that ACPC model intercomparison case, which Sue just discussed. And we use Wolfgang coupled with spectrum beam, which means the chemistry on the aerosol are predicted. And we get, this is a Houston produced 1 order of magnitude higher aerosols. Those ultrafar particles is very large as well. And the simulated storm actually very close to the observed storm. And the strongest storm occurred at the urban rural boundaries. This is because of overland effect, which detailed in our paper. And I want to mention here, if we look at the aerosol effect, it's significantly increased vertical velocity for this larger vertical velocities, and reduce the occurrences of this lower updraft velocities. So is the enhancement of the precipitation, which is almost by 30%. And this is started from mixed phase stage. The aerosol increased the updraft intensity, and because of the buoyancy increased, and many because of the latent heating from the condensation. So this increase is from condensation heating. The up level, cold phase heating increase, it's much higher level and also small. And this actually accelerates the cloud developing into the deep cloud. At deep cloud stage, the aerosol effect is more significant. This is because you can see the condensation heating is enhanced much more. So now we have this exciting trace field campaign, which will occur in a couple of months. I would like to, we will have this exciting data about high frequency measurement in cloud microphysics, the same dynamics and aerosol. But I want to mention a few challenges here. First is mingled with the urbanization impact, because the site is at the metropolitan area. And we showed that the sea breeze circulation is enhanced by the overland effect. And this actually invigorated shallow clouds and accelerate the development into the mixed phase stage. Also, the aerosol effect and the urbanization effect can work together. They can have a nonlinear amplification effect on the heavy rain rates and the strong updrafts. So the aerosol properties of Houston also could be more complicated. The load is too high. If we have absorbing aerosols, they can suppress convection in Houston, which is counteract with the invigoration effect. And also, like Sue mentioned, we want to find the number of cases with from clean to polluted with similar meteorology, but it might be difficult over Houston because overall it's pretty polluted. Thank you.
Right, so I just wanted to mention at outset that this isn't work that is being funded by ASR in any way. Not that I wouldn't take it, but I also haven't applied for it. It's just I'm submitting this in kind for enhancing the discussion. And I want to also highlight really that this is work that's been done by an undergraduate working with me, Christine Neumeier, together with Bob Holtzworth, who runs the Worldwide Lightning Location Network out of Earth and Space Sciences, as well as Dae-Hyun Kim, faculty member in my department, and then a graduate student, Wei Cheng. let's see, try to advance my slide. Okay, so just a brief synopsis of lightning and why it is kind of useful as a metric, and it's been used for many years now as a metric of convection intensity. It's, of course, a function of updraft velocity and mixed phase microphysics, and that's related to the generation and sustaining of the charge separation through processes involving riming and collisions between graupel and ice crystals and the separation thereof by the updrafts. And so lightning can be used as an indicator of storm vertical development intensity, as well as deep convective cloud microphysics. Although the exact combination of these ingredients in terms of how they relate to something like the lightning flash rate or stroke density is not well understood in detail. Excuse me, but a common and nicely simple parameterization for lightning flash rate developed by David Romps uses just the product of convective available potential energy, or CAPE, and precipitation rate. The idea being that for storms identified and scaled by precipitation rate, higher CAPE will lead to stronger updrafts and therefore higher development in altitude of the storms, and thus more likely higher lightning. And in spite of its simplicity, it does relatively well, actually explaining spatial patterns of lightning and about 30% of the variability of lightning over land. However, it doesn't do so well for lightning over ocean. And moreover, it's obviously lacking any possible effects of aerosols on deep convective cloud microphysics, which might affect the charging and also the latent heat release and so on that we've heard about already, as well as potential feedbacks through perturbations to the transport of moisture, impacting humidity aloft of the boundary layers recently suggested by Abbott et al. And so we've been examining some natural lightning laboratories, if you will, in the region of the Indian Ocean and the South China Sea, around the maritime continent. And in our previous papers, we noted that there was enhancement in lightning stroke density that occurs centered over two of the world's busiest shipping lanes that I've highlighted here in red, in the Indian Ocean and the South China Sea. And in those two papers, we found factors of 2 or 3 enhancements in the annual mean lightning compared to those reference boxes that we've chosen adjacent to the shipping lanes. And we hypothesized in those papers that this was due to enhanced aerosol concentrations from ship exhaust. And we followed it up with an idealized cloud resolving modeling study that generally supported that hypothesis. However, we did not examine in detail the interannual variability in this enhancement, or how other factors like CAPE, wind shear, low level stability, and so on might covary and affect the degree of this enhancement. So here I'm showing 10 years of the lightning stroke density data from the Worldwide Lightning Location Network, plotted on the 2-dimensional space of precipitation rate from the IMER database and CAPE to the 1/2 from the ERA reanalysis for the Indian Ocean shipping lane in this first column, and then the southernmost reference box we chose in this central column. And then the last column is the difference between these two. So the lightning stroke density is the heat map. So the coloring, that is, and this allows us to directly compare then the lightning stroke density for different CAPE and precipitation rate regimes between the shipping lane, which has a persistent aerosol perturbation, and an equivalent size region adjacent to the south. And the point here is that in the active season, which does vary with location as you go northward in latitude, so it's a little bit hard to do an apples to apples comparison, but for the active season of the shipping lane from about November to April, what you see here is that we always have, essentially regardless of what the CAPE is, both in the annual average and any season, CAPE or precip, we have 100 to 300% enhancement in lightning stroke density over the shipping lane compared to that reference box. So that is, if our hypothesis that the enhancement is aerosol driven, then there's no CAPE or storm size threshold for the aerosol effect on lightning to be induced. And moreover, CAPE times precip, therefore, doesn't predict the lightning stroke density in this region. And if anything, it would actually overestimate the lightning stroke density. And that suggests that there are other limitations that are important, especially over the ocean. And aerosol could be one of those. So we get a slightly different picture when we compare to the northern reference box north of the Indian Ocean shipping lane, and only different in the sense that, again, during the active region, we still get enhancement at any cape or precip where we have similar overlap. But we do actually see that while the difference is persistent in the annual mean during the region of intense convection in the northern region, the Bay of Bengal region, we actually see that there is more lightning for the same cape and precip regimes north of the shipping lane. That is, the shipping lane does not show an enhancement. In fact, it's lower lightning than in this region. However, I could also argue that this too may be due to an aerosol enhancement of lightning just north of the shipping lane, because on average, there is a significant gradient in the optical depth from north to south. And finally, we can look at the South China Sea shipping lane. I'm not going to dwell on this, but you see again, very clear enhancement at all cape and precip values that the shipping lane here has much higher lightning. And that would suggest then that these this region is affected by the ship pollution quite dramatically. And while these can be used to further improve our simulation of convection, especially of lightning parameterizations, improving the lightning parameterizations, assuming it's a physically realistic way, would then imply that we're capturing the effects of aerosols and storm vertical development intensity. And I do want to point out that if you kind of squint, you might see perhaps greater enhancement in this particular region of lightning actually at lower cape and lower precipitation values, which is something that you might expect where the aerosols might invigorate the storms to a greater degree when you have less driving factors. But to finish, I want to point out that there's obviously seasonal variability to this enhancement. And a lot of what Christine has worked on is actually the interannual variability in the lightning enhancement, which is rather substantial, but I don't have time to show. But one of the things that we have found that can explain a large fraction of the variability in this lightning stroke density enhancement is simply the number concentration of aerosol particles greater than 40 nanometers in size. In this quantity here, N40 is actually predicted from a global chemical transport model driven by reanalysis meteorology. It can be taken with a little bit of a grain of salt, but it explains better than cape times precip the lightning frequency for a given cape in this region, in particular the South China Sea shipping lane, where we're explaining about 40% of the variability in lightning strokes alone without any input of environmental factors like cape or precip. And with that, I'll stop.
Excellent, Joel. Clearly, kind of new discovery of a few years, and it's come a long way. So we'll talk more about that.
Okay, thank you, Jinan. Yeah, I'd like to acknowledge my co-author here, Toby Ross. He's an excellent master's student.
Sonia, it looks like you did the swap display on the top.
Oh, sorry. Now are you seeing it?
Yes, good.
I'm sorry. Okay. I'd like to acknowledge Toby Ross, who's a master's student working on this project with me, and he's done all the work, and I'm just kind of supervising here a little bit. So we were trying to build on a recent result that we had with our former ASR work. So we had been looking at microphysical influences on cold pools, and we were just trying to generate in a single environment a whole bunch of different realizations with CM1 and then kind of study the cold pool effects. And this is a plot of the onset time of the cold pool from an NCS that we simulated with CM1 versus very different simulations that we had done with different microphysical aspects. And as you'll see, nothing really changed the onset time of the cold pool very much, except curiously the CCN number concentration, and basically increasing it from 350 to 400 per cubic centimeter delayed the cold pool starting time by about 2 hours. And that wasn't the main focus of that study, but it was a curious result. And we wanted to dig into it more. We hypothesized, of course, that this effect is due to the speed of the warm rain process influenced by the CCN, so that higher CCN would delay the warm rain process, and thus it would delay the timing of the first rainfall to the ground that could help make the cold pool. But we now wanted to go on and say, okay, so we know this happens in a model in a single environment. Let's try to use some observations that happen in different natural environments and see if we can still see this effect.
So we went to cacti, using cacti data, and we're trying to assess the speed of the warm rain process on different days, and then look at how soon the cold pools initiate on those days. So for the first part here, those of you familiar with cacti, the G1 was flying and targeting the shallow convection that was safe to pass through. And so they quantified the clear air CCN on each day and the hydrometeor concentrations and sizes within those shallower clouds. And you can see the flight patterns here on the right, but that was only occurring in the earlier shallow convection. Then of course they had to divert off, and we can only study the deep convection with radar. And so Toby's been doing that. And although there were many cases with cold pools during cacti, we were trying to isolate it to specific instances where there were no interactions of cold pools, where we could trace a single cold pool back to its single storm origin. And so that reduced our cases to about 3 well-observed cold pool cases, where we were quantifying the cold pool onset time by the 30 dBz echo, kind of using that as convective initiation time, and then looking at the cold pool on the radar, as like you can see in this bottom velocity plot there briefly. Toby will go through all of this and the procedure at the poster session on Wednesday, but suffice it to say right now that 2 of these cases agreed with our hypothesis and 1 does not. So here's the results he will show. And I want to spend this time talking about the December 5th case, because we have an interesting question to pose to you all, and that I think may also be relevant for those of you that are going to go to Tracer. So on this December 5th case, there was an inversion, unlike the other 2 cases, and we pointed out here in the sounding. And so when the aircraft was sampling the CCN, at first they're at higher altitudes and we're having lower values, maybe around 500 or 400 per cubic centimeter. And then when the aircraft, of course, goes beneath the inversion, they hit higher amounts of CCN, about 1300 per cubic centimeter. So what we see is that the early clouds that that the aircraft passed through and sampled are consistent. The warm rain process is consistent with a faster warm rain process due to lower CCN amounts. And we think because these little clouds are forming over the terrain, they're only accessing, they're weaker, so they're only accessing the air above the inversion height, and thus the lower CCN values. But we think that as this convection deepens, it starts to move down the mountains. And also, as it strengthens, we think it's pulling up now air, ingesting air from beneath the inversion height that would actually warrant calling this a high CCN case for this bigger storm that actually put out the cold pool we're studying. And I've just got a quick radar snapshot here on the upper left. This is where the location was of the original cloud early in its lifetime. And then later on the right, you can see that it's deepened substantially, and it's also kind of moved down the mountain somewhat. And so we think it's accessing, both higher Cape air because it's extending to higher altitudes now, as well as higher CCN air, and that this should actually be considered a high CCN case. I think this could be relevant for discussions about tracer, because as you have in the Houston area, as you have a sea breeze move in, you're also going to have these transitions between high CCN and low CCN cases that you're going to have to think about as well. And with that, I'll stop there. Thank you.
Great, thank you, and I'll try to be quicker. So here, this ties in nicely with Pengfei's work and some other work he's doing. So just to cut to the chase, I'll be presenting evidence of a large SOA formation by vapor condensation and PyroCb outflow, both in LES simulations of this British Columbia fire that injected a lot of smoke into the lower stratosphere and upper troposphere. And this work is aligned with ASR ARM, but it is funded by Los Alamos, but there's alignment with black carbon and other things in the atmosphere. So just to summarize, I'm not a modeler, but I do understand what models do. So if you look at sort of dry deep convection, you have this pyrocumulonimbus domain, and LES models do capture all the physics. On the left-hand side, the cartoon is basically the PyroCb dynamics. And you basically need a dry troposphere, a lot of fuel, a boundary layer, a lot of fuel, dry boundary layer, and then you need a moist upper atmosphere. And under those conditions, you get a lot of smoke up there that can be kicked up further. And obviously, aerosol lifetimes in the troposphere of the order of a week. They can go global, but if you get into the stratosphere, you get into year time constants. So that does extend couplings of smoke to climate. Jevin already showed this aerosol microphysics, this intensification. So that's also solid in most models. What is the third leg of this is chemistry. And here we have a cartoon of, when you have fires, you emit not just primary organic aerosols, but also hydrocarbons of the same scale. And so these hydrocarbons can actually, non-methane hydrocarbons in the updraft, if it's cold enough, they can condense. And I think I'll present some data. It's been talked about by Murphy, so conceptually exists, but at the end of the day, we need to get data to prove what is happening where. So just a cartoon of, I think we've seen a lot of fires in the news, but what I'm summarizing here is sort of a comparison of stratospheric mass injection between volcanoes and fires. And if you look at the Pacific Northwest British Columbia fire in 2017, there were actually 4 to 5 PyroCbs, and over a period of several hours, they injected about 0.0 teragram smoke into the stratosphere. There may have been some lofting also, but essentially it's a pretty intense injection, and you can see this in the Himawari images up there. So you can see the pyrocumulus pumping up into the coal tops in the stratosphere. And so what we did, now it's very hard to plan for these field campaigns. Actually, FireX AQ happened, and they thought they got one, but actually their inlet got samples, so Shuka was really disappointed. But anyway, what we tried to do is, since this data is available, we tried to simulate it as best as we could and do some closure. And here I'm showing you a couple of examples. First is there was some uncertainty on the fuels. There were pine beetle kills in that area. So there was actually a lot of slash piles that weren't removed. So the fuel distribution was very complicated. And so we tried to capture that as best as we could. And so the questions we ask is, how was PyroCb lofted into the stratosphere so fast? And this is both direct injection, also self-lofting by solar heating if the plume is high enough. And why was the smoke mass so much higher than fuel loads? And so it's a complicated story. And you can see we use realistic fuel roads, heat maps. And if you look at the simulation in the third on the bottom, we try to realistically capture the spatial temporal evolution of the observed pyrocumulus. So we do an informed model. I wouldn't say it's a constrained model, a pretty well-informed model. So here's the results, where I'm showing the mixed fuel load with aerosol cloud interactions that enhance smoke lofting into the UTLS. And on the left-hand plot, you're seeing in the solid line, the different scenarios. The first is forest in the yellow, and that's forest has higher fuel load and they burn faster. Then you have slash, which are basically logs sitting in bunches. They have low fuel load, and the mixed is in between. So if you look at the model, you actually get a time evolution. With time, you get more and more smoke accumulating. But the point to note is that the model is actually below the observations, and by a factor of 2 or so. And so that's the left-hand plot. The right-hand plot, Sue already showed a nice diagnostics of this. But what we do is we basically turn the cloud ice, warm cloud microphysics on and off. And we can see basically a 4-kilometer further rise of the smoke by latent heat release. And this actually begins to enter the stratosphere. It's still a tail. We don't have these deep convective systems, the fidelity to do the stratospheric, penetration. But I think the smoke does rise up there. But there's still, in these things, if you look at the output, the simulations, aerosols are still below the observations by a factor of 2. And so what we did here was, and Kyle Gorkowski kind of did the quantitative treatments, but essentially we put non-methane volatile organics into the model, and we allow for SOA formation while condensing organics in the cold updraft. So it's a PDF for a idealized, organic. So there is some tuning going on, but essentially what this shows you is there's a factor of 2 to 3 increase in secondary organic aerosols. And that is real, and actually associated with that, the BC fraction goes down actually because of that same effect. So these are observed, and this is again modeled very coarse, but we did try to get some real data from FireXAQ. And what you can see here is that actually the BC mass, as you go up on the left-hand side, goes down with altitude, consistent with what we would expect. The mean diameter actually goes up on BC, but what's most important is actually one nonene actually begins to show increases in the upper troposphere. So show decreases. So one nonene is a gas that actually has a dip at 10 kilometers, and it's being converted to secondary organic aerosols. So I think this gives you some observational evidence that there is at least one nonene is converting to secondary organic aerosols, and then we can use a model to start simulating these effects. Finally, we've put this thing into a global model, and I'm not going to go into this in detail, but this has been observed from satellites. But we can, in a global model, represent and reproduce the observed rise rate of the plume, both with GEOS 5 and also with CESM Karma. And it's about 1 kilometer or so every few days. And finally, the lifetime of the stratospheric smoke is about 5 months, and it's consistent with several papers that have appeared. So I'll just close here that PyroCb significantly enhanced aerosols in the UTLS, and these processes are missing in current models and will bias forcing. It complements what was shown earlier, that you get lower forcing. So you've got these wet systems that probably are continuous, more regular, and then you have these dry systems that can offset some of the tech. We did LES simulations. The key finding here is really that SOA formation via organic vapor condensation, the cold updrafts, is the biggest lever arm. And since it's hard to plan for PyroCb, we probably need to be creative. And to the best of my knowledge, there has not been a direct sampling of a PyroCb with the SP2 and the SPAMS on. There's been some indirect sample. So I'll stop here and hand it over to Joanne.
Great. Thanks for the chance to share a little bit of what we're thinking about with respect to light absorption and water uptake, and then implications that has for things like atmospheric stability. And so I think that this has some relevance to what we've been talking about with convection. And the key question here is how liquid water affects aerosol absorption. And then tying into that is how that depends on the particular properties of your absorbing aerosol, spanning from black carbon to brown carbon and the various things that it might mix with in the end, and whether you have soluble or somewhat soluble materials in the end. But I do want to thank my co-PI Chi Zhang and the graduate student, new graduate student working on this, Rachel Del Porto, and my collaborators at LANO as well. So I'm not very good at drawing cartoons, so I'm going to use some art to illustrate kind of the semi-direct effect here, right? So we have two things that we're thinking about with respect to the influence of light absorption on things like convection. And that is the cloud burn-off effect that you might get from aerosol light absorption within clouds, whether that black carbon is contained within a cloud droplet or just in the very humid environment and the interstitial spaces between cloud droplets. But also if you have absorbing species, they can suppress convection overall, which can influence convective cloud formation. And I think Jinan mentioned the importance of that earlier as well. And so really what we're interested in here is this kind of semi-direct effect. And thinking about, a lot of this is going to take place in fairly humid environments in the end. So really understanding the role that water plays on absorption is important. And just as a framework, right, over the past many years, people have been working pretty hard to understand the influence that non-water coatings can have on, say, absorption from black carbon. And we've now been able to show pretty well that, in various contexts, that these non-absorbing coatings can significantly enhance absorption, although it really does depend on the mixing state distribution that you have across your population of particles, what you're going to observe in the atmosphere in any given environment. But this is kind of our starting framework, is from the non-water coatings. But what happens when we bring in water? Well, this is where it's really going to depend on the presence of those non-absorbing coatings, whether they're hygroscopic or whether they're not so hygroscopic in the end, whether they're going to take up water in the end. It's going to depend on what those absorbing species do when you have water in the end. If they're non-hygroscopic, they might say partition to the surface or be excluded from those water areas. Water may not exactly act like a coating, which is what's going to give you the strongest enhancement that you might get in absorption. So and this might depend then on the internal morphology that you get overall. So this is really going to depend on kind of the complex interplay between all the different components that you have across a population of particles. And there are some models that, models include this effect in various ways, and some do predict or indicate a very large influence of condensed phase water on absorption by black carbon. And so here's a nice example from Laura Fierce, looking at the influence of relative humidity here on absorption. And you see these increases, especially at high relative humidity, as you start to move towards cloud conditions. And you see when you have a more hygroscopic component here in blue, you get a bigger impact than if you have a less hygroscopic coating material in orange. But then we also have this kind of counteracting effect where the more of a coating that you have, so the more stuff that you might have that can take up water, you start potentially from a higher value in terms of your enhancement in the first place, which can actually change the delta that you might get from water uptake overall. And so really piecing this together experimentally is necessary to really validate some of these model predictions in different ways. And so far, there really is fairly limited experimental validation, in part because of experimental instrumental challenges. And so we've been working hard to overcome some of those instrumental challenges, and we're now applying some of this in the lab and with the potential to move to the field. And I think that these are really complementary approaches, and I'll show some of our lab results here in a minute. But really, this is what's going to give us that kind of foundational process level understanding that we can link to our observations and test. And that's really because we can look at controlled and well-defined systems spanning from very simple to complex, right? We can pick very black things, different brown carbon surrogates, different types of coatings that we might mix together. And this is going to really provide the foundation for testing existing theories and expanding these to develop new parameterizations that can prove to be robust in the atmosphere. But of course, in the field, you start to get much more complex real-world behavior, mixtures of different particles, much more complex populations of particles that are time evolving overall. But really, it's these types of field observations that we're going to make in the TracerCat campaign in Houston next summer that will really allow us to test and refine our lab parameterizations. But also the field gives us the fun challenges of new instrument deployment. And so we're excited to actually overcome some of these challenges by next summer and be ready for everything. So where we are right now with some of our lab observations. So on the top, I'm showing some examples from fullerene soot mixture. So this is fullerene soot's a very dark absorbing species, and then we can mix that with, say, ammonium sulfate. And we see that as we start to increase humidity, the absorption that we measure goes up, as well as the scattering and the extinction. Overall, if we mix things with nigrosine, which is still a strongly absorbing species, but much more soluble, we get different behavior. Depends on whether we mix with glucose or what it is. But overall, we start to find pretty strong relationships between how absorption changes with water uptake and how scattering changes with water uptake. That is going to provide the basis for development of parameterizations that we hope can help with some of the modeling efforts. And so I'll finish there just to say, we need to improve our understanding from an experimental standpoint of water uptake on aerosol absorption. Complementary lab and field approaches can really help, and our lab observations are already suggesting water uptake does affect absorption, but it really depends on what we mix together, and that's what we really need to explore further. So thanks.
Okay, everybody, I hope you can see my screen.
Yep, we can. You want to go presentation mode? Yeah, now we are good.
Okay, fantastic. Let me just turn on my laser pointer here. Okay, I hope you can see that. So this is work led by a postdoc, Prashant Prabhakaran, and was part of an ASR proposal led by Will Cantrell. What I'm going to tell you about is sort of a revived idea that's been around for a long time in the cloud physics community, and that is that when you have a drop, for example, a supercooled droplet that freezes, it releases some latent heat, and that can result in a local supersaturation. And the difference here is that this process is happening in wakes of hydrometeors, and therefore can expose a significant amount of the cloud volume to high supersaturations, certainly high ice supersaturations, and often high water supersaturations. That could have implications for both ice nucleation and cloud invigoration specifically through the possibility of activation of large numbers of ultrafine aerosols, similar to what Jinan and others have spoken about. So the physics depends on two basic ideas. One is that you need a hydrometeor that is not in thermal equilibrium with the environment. Examples of that would be a rhyming ice particle in a supercooled convection region, or a melting ice particle below the 0 degrees Celsius level. The other essential piece of the physics is that these hydrometeors need to be falling rapidly and therefore leaving a turbulent wake. And that wake, of course, consists of warm, humid air in the rhyming particle case, mixing with a relatively cold environment. And that isobaric mixing can lead to large supersaturations. So we tested this and basically demonstrated that the effect does happen. This was done in the Michigan Tech Pi chamber. This is a schematic of how the experiment was set up. Basically, we create a laser light sheet, and then we let a relatively warm water droplet fall through the environment, and it leaves a wake. And if we seed that environment with aerosol particles, if that wake is supersaturated, the aerosols will be activated. And we can do that both under warm and supercooled conditions with aerosol particles that may be ice nuclei or not. And then we look at the scattered light from the wake. So basically, we put ourselves in the reference frame of the wake rather than in the reference frame of the falling drop. And that allows us to see how the system evolves. So I want to show you this video. This is, I hope that's coming through. I know videos sometimes struggle, but what you should see on the left is a drop falling through and leaving a supersaturated wake, and you see a pulse of activated cloud droplets in that wake. Let me just stop and ask somebody if you can tell me if you can see that video.
Yes.
Awesome. Okay. So of course, in this case, the cloud chamber is slightly subsaturated because we didn't want to activate all of the particles, all of the aerosol, and that's why the wake dissipates relatively rapidly. But in a real cloud, of course, you would have the already activated and growing cloud droplets, and a falling rhyming ice particle, for example, would leave a supersaturated wake and would activate any ultrafine aerosol particles that are possible to be activated at that level of supersaturation. I'll just show you one more. There's a little bit of a slowed down view, and on the right here, you can see silver iodide particles being nucleated into ice. That's in this right panel. which played once, but I can't get it to play again. Sorry about that. So these videos are just simply to show that the mechanism really does work in the real world. The actual supersaturations that are achieved depend on the temperature and the humidity in the environment. And I won't go into details on that here. But the really critical thing is to think about the rate at which the cloud could be exposed to these high wake supersaturations. If it's just a very local phenomenon, then it's a curiosity. It's cool, but it's just a curiosity. If a significant amount of the cloud can be exposed to high wake supersaturations, then it becomes more than a curiosity and perhaps something that should be parameterized and put into models. Since obviously the physics involved here is unresolved even in a relatively high resolution LES, convective cloud. So what we have here is the volume rate swept by a hydrometeor. This is kind of standard. You have a cross section, a fall speed, and then some efficiency of the wake growth, mixing of the environment. We can make some statements about that, but I won't go into that now. And so then you can get the total volume swept by hydrometeors with concentration N. So for example, rhyming or Grapple particles. And so you could calculate the total number of aerosols exposed to very high supersaturation, or alternatively, you can use this to get a time scale for exposing the cloud volume to its saturated wake. So it's essentially a rate at which you expose volume to this high supersaturation. And using what, let's say, quote unquote realistic. So if we just grab Krupacher and Kletter, Rogers and Yao and look up kind of typical Grapple size distributions, we calculate tau of 100 to 200 seconds. So is that reasonable? Here's an example. This was done with Christoph Sievert at the German Weather Service. They have this nice convection model that has Lagrangian ice particles. It's called mixed snow. And you can see there's an updraft region here. This is just a snapshot. And so we've taken this just as kind of a sanity check to see if this idea could expose a significant amount of a squall line to high supersaturations. So here I'm showing total water content. And on the next slide, I'm going to show this rate parameter, basically the time scale for exposing cloud to high supersaturation. So to do that, we've taken these Lagrangian ice particles and we've asked, okay, where do I have ice that is either rhyming or ice that is melting and is therefore out of thermal equilibrium? And I know the fall speed of those ice particles, and because they're Lagrangian, right, I have all of that information. I know their concentration, and I can see how that all plays out. So again, pay attention to the fact that this is where the updraft is. So you can see here's the updraft region where they're rhyming particles, and then these are the particles falling out that are melting. These rhyming particles, the tau value, this rate parameter, I guess, estimated there is, of order several minutes, which is same order of magnitude as the residence time of a Lagrangian particle in this updraft. So effectively, although it's a relatively small volume fraction of the whole cloud, essentially anything that goes into the cloud has to move through this region. And the time that a typical air parcel spends in this updraft region where there's rhymers present is enough that essentially all of that cloud would be exposed to this high supersaturation. So
wrap up time.
Okay, yeah. Just the, I guess it's just a call for collaborators or ideas. We're open to ideas from any of you on whether this is something of interest and could be relevant to the convection, invigoration problem. Thanks very much.
Yeah, so Dubey and G1 asked me to give a little update today on the LASSO cacti scenario. So actually, I'm a little different than some of the other talks. I'm not going to be really discussing aerosol details because the LASSO scenario we're doing at this point, we're just using the prescribed CCN with the Thompson scheme. We're not looking into the details of the aerosol, but these are a lot of simulations that could become available for the aerosol cloud modeling community that they can build upon and really take advantage of. In a group this size, not everybody might know what LASSO is. It's a complicated acronym. It stands for LES, ARM, Symbiotic Simulation and Observation. This is an activity within ARM with the goal of using high resolution modeling to bridge gaps and scales and help add context, observations, and kind of in the big picture to just give a lot of extra value to ARM's observations and make the observations more useful for researchers. So we've been doing this for shallow convection for the last 5 years, and now we're turning our attention to deep convection and using the cacti field campaign as a place to do that. So ultimately, our goal is to generate about 10 case states worth of LES simulations for the cacti field campaign. And on the right here is just a quick map that's in this Argentina area of the cacti campaign. So this is a plot that I've shown at other breakout sessions earlier, but just to give a little context, those of you that are familiar with our shallow convection LASSO work, that was basically just done at the LES scale. With the deep convection, we're actually approaching this very differently. And the modeling now is going to be a multi-scale modeling approach available to the community when we release it. So basically what we're doing first, we have about 20 case states we're looking at as possible dates we'll be simulating, and we'll be downsampling to about 10 case states from those. We're running mesoscale ensembles right now, so we have an initial mesoscale ensemble complete for those 20 case states, and it's about 33 ensemble members for each case. So that's based on the Aero5, the Aero5 ensemble, the FNL and the GFS ensembles. And as you can see on the right, that gives quite a variety of a convective response depending on the boundary condition that's used with the model. And these simulations, we refer to these as the mesoscale simulations, and it goes down to about 2.5 kilometers grid spacing. From these, we're working with the GOES 16 IR data to basically identify convective areas and things like that, to then down select what are the couple best ensemble members for each case state of interest. And then those will be used for the actual LES runs. Once we do that, we'll move forward with the LES, but we're still going to make available these full ensembles at the mesoscale. So that's something that's very useful, I think, for the community, because now we'll have these different boundary conditions and a much wider range of convective modeling coming out of the simulations that people can use to look at cacti in various scenarios. And there's a lot of research that could be done just with these mesoscale ensembles as well. Just very quickly now, moving on to the LES simulations, our goal is to get LES down to 100-meter grid spacing for the case states that we select. And we'll probably have 2 to 3 LES simulations per case state that we ultimately pick. The ultimate number comes down to the available computational resources. We're going to be doing this with more like a weather forecast scenario for WRF. We'll be using 4 domains, the mesoscale domains for the first pair, which will run, and then we'll use WRF's end down to get the final pair of simulations with LES physics to get a 500-meter and a 100-meter grid spacing. On the right's one example. We've been using the January 25th case from cacti as one of our test dates. So we have several LES simulations complete for that already. I mean, you can see here, the top row is the mesoscale runs, and the bottom row is the LES runs for this case. The star is the AMF location, and the contours are the terrain. So one of the first things you'll notice is we go down to the higher resolution, and it's nothing shocking, but basically you get much higher detail in your terrain, which makes it much more accurate in terms of where the convection could pop up due to terrain forcing and things like that. And the other thing you'll notice, there's a lot more detail in the up and down drafts. The shading here is the vertical velocity at 500 millibars. And one of the things that really strikes me, just going from 500 meters, which is the grid spacing that was shown in a lot of the earlier talks today, down to 100 meters, the extra detail you get in the updrafts and downdrafts is amazing. It looks so much more realistic at 100 meters. And I believe the physics and the science that we're going to be able to do with that is so much more useful and more informative than at the more terra incognita grid spacing of 500 meters. One of the things that really stands out on these 500-meter runs, you're still kind of more blobby in terms of the structure of the convection. I mean, you see very clear rings of downdrafts around the updraft regions, whereas when you go to the 100 meters, you get more of that kind of turbulence look to it. So I don't have a lot of time today. This is just an overview. We're going to have a much longer talk tomorrow at the deep convection breakout where we can have more discussion and things like that. So I'm not going to dwell on this today. But one of the things I would like from the community and for you all to be thinking about is what is it that you would like out of these LASSO simulations that would really help your research? At this point, we really need to lock down what are the output variables we're going to be doing and the frequency of those outputs. So that's something I want feedback on. So if you have interests in that, please get back to me. And we have a new forum we've actually set up. The web address is green on here, discourse.adc.arm.gov, where you can go in and post and we get interaction with the community. So we think this is a really useful way we can start getting feedback on this. So check that out and start sharing with us your thoughts there. And also I wanted to note, coming up sometime this summer, we don't have a date set yet, but we're hoping to have a LASSO cacti online session for an afternoon to talk a little bit more about the details and to kind of get all this detailed information out to the community and so we can lock that down for the production runs. So my time's up. So at this point, I think it's time to move on.
All right, good morning from West Coast. And in this talk, I'm going to talk about the aerosol convection interaction in GCMs. And actually, it really should be aerosol effect on convection because it's a one-way. So I'm going to look at some of the results from CAM5 as well as DOE model. Okay, aerosol effects on convection, cloud model simulations, and the results vary. And as you can see, you saw from Sue's talk earlier today, and observations, there were a few beginning in 2004 by Andrea, and then Zhang and Li had some, and a few others, and including Tracer in the future. But in terms of GCM simulations, there are very few. I think probably one or two at most. So we did a little bit of work on how aerosols affect convection GCMs, and this is a microphysics scheme that we use for convection, and the aerosols affect clouds through ice nucleation and droplet activation, and through a bunch of microphysics processes. So getting to the model simulations, we used CAM5, which use MG microphysics, and PARC and Bretherton shallow and PBL convection. Whereas for E2SM V2 plus P3, we use P3 microphysics and a club for PBL and shallow convection. So the way we did was just around the simple control simulations with whatever the aerosols are in the models, and then we bump that by an order of magnitude 10 times. But then that's only used to diagnose one-time step effect on convections. So it's like a single column model simulation, or sort of piggybacking, as Hugh mentioned in his chat earlier. And finally, we run this fully interactive, but aerosols only affect convection. That is, outside of convection loop, we turn it off with whatever the aerosols are in the model. So to show this CAM5 simulation in this diagnostic, that is aerosols only effects on convection are only diagnosed. The left is tropical ice water heating rate, and the blue is from the 10 times diagnostic aerosols, and you can see that the heating is enhanced and the mass flux is also enhanced, and The right is on mid latitudes, and the effect is a bit smaller than compared to the tropics. And then we looked at the effect on precipitation. The top is the control around precipitation distribution in the CAM simulation. And the middle is a difference between 10 times diagnostics and the control. That is, when I say diagnostics, I mean, we use identical thermodynamic conditions to look at the invigoration. As you can see that of the ITCZ regions, the aerosol effect to enhance the precipitation, and at the bottom is a fractional changes, and in general is enhanced, but then over these stratiform cloud areas, that's decreased. And then when we put this in the full interactive mode, this top is shows the difference between the 10 times aerosol and the control precipitation, and it's much smaller. It's, I think the change is about order of 1 millimeter per day. And the bottom is a difference between the control and different other simulations. In the case of 10 times in diagnostic case, you have enhanced precipitation of the tropics. But then once you have fully coupled simulations in the atmosphere, when I say fully coupled, I mean a coupled aerosol with the atmospheric circulation, the change is minimal. So really the immigration effect is much smaller. So the same thing is seen in E3SM, and the top is the control around, the middle is 10 times aerosol, again in this case interactive, and then the bottom is difference. And again, the difference in terms of precipitation is about 1 millimeter per day, but then the patterns are quite different from what we saw in the CAM around. So there is a sort of a large difference among different models. So we looked at the cloud droplet. Let me see the autocommotion rate. Yeah. The red is the control simulation, and we see that you have sort of autocommotion in the lower part of the troposphere. Then by activating, I mean by including more aerosols in the diagnostic run, you have this substantially reduced autocommotion in the lower troposphere, but then it increases in the upper part, which is understandable because you have smaller droplets being lofted upward, and then also you have yeah, I think the droplets are lofted, therefore you have larger autocommotion rate in the upper part of the warm cloud area. And then by using interactive aerosols, you see slightly enhanced autocommotion rate again, and a similar patterns in the lower part. You have reduced the aerosol, reduced the autocommotion rate. So just wrap up, the connected microphysics scheme enables us to look at the GCM, to look at the aerosol convection invigoration and GCMs. And then for fixed meteorological conditions, connected microphysics can simulate the aerosol invigoration effect on convection. But when large-scale circulation is allowed to respond to the invigorated convection, the aerosol invigoration effect is much smaller, and similar results are seen in E3SM. Thank you. I'll stop here.
My name is Ling Ling. I'm a graduate student at Texas A&M University. Thank you very much for the opportunity. In today's talk, I would like to highlight some of our research of the improved parameterizations of cloud microphysics and aerosol wet removal in deep convection for global climate models. In the bottom, I would like to acknowledge my co-authors and the funding agency. A brief motivation. We all know that the convection is an important component in our climate system. They can produce spatially extensive annual clouds, which impact radiative energy budget. They are also very efficient in aerosol transport and removal. Also, they are key component in the precipitation processes. However, convective cloud microphysics is overly simplified in most of the global climate models, which might induce large spread and uncertainties in the simulations of iceberg content across models and their atmospheric aerosol distributions in large contrast to observations like I show you in the top. Thanks to Sonia and Zhang's work, they developed a convective cloud microphysics scheme based on their large-scale cloud microphysics scheme for use in global climate models. We further improve the parameterizations of cloud microphysics and aerosol wet removal in deep convection for global climate models. This slide shows you a schematic diagram of an improved double moment convective cloud microphysics. The original convective cloud microphysics from Sonia and Zhang 2011 is shown in black. We further improve and expand the convective cloud microphysics, which is shown in blue by parameterizing cloud ice to fall based on the Davis and Reynolds number parameterization by replacing the original snow terminal velocity with a physically based terminal velocity scheme. And third, by considering convective snow to detrain and fit large-scale clouds. And finally, by adding a grapple category with a set of grapple microphysics. This slide shows you the vertical profiles of frozen water content from the single column model simulation in the left and global simulation in the right. We define frozen water as the sum of the suspending and precipitating ice. I would like to pay attention to the blue curve, which is the experiment we consider the grapple microphysics. As you can see, the incorporation of grapple microphysics reduced the overestimation of frozen water content in better agreement with satellite retrievals, which is shown in the black dash curve. While the default model tend to overestimate the frozen water content, the global simulations also show a similar degree of improvement over the four convective regions when compared with the classic Calypso derived deep convective frozen water content. Let's switch gear a little bit, talking about aerosol wet removal. In the default model, aerosols are prescribed to activate to become convective cloud-borne aerosol, which undergo wet removal through precipitation processes, which is implicitly parameterized. The remaining cloud-borne aerosol will resuspend in the atmosphere. I believe we all agree that cloud microphysics is important for aerosol cloud interactions. So with the introduction of a detailed convective cloud microphysics scheme by Sonia and Zhang 2011, most of the physical processes can be represented explicitly now. Aerosols are activated through primary and secondary processes to become convective cloud-borne aerosol. Wet removal is explicitly parameterized through the microphysics-based precipitation initiation and generation processes. We further consider rain evaporation and Bourgeois resuspension to release aerosol back into the atmosphere. The remaining cloud-borne aerosol will detrain to larger scale clouds in a consistent manner with cloud condensate detrainment. This slide shows you the vertical profiles of black carbon and sea salt concentrations over the Pacific and compared against the pole-to-pole observations from the HIPPO and Atom Field campaign. The blue curve is the experiment in which we incorporate all of the improvement in the aerosol wet removal scheme. The improved aerosol wet removal scheme reduced the overestimation of black carbon and sea salt by a factor of 10 and 1,000 respectively in the atmosphere, in better agreement with observations. While the control simulation, the default model, and the other model configurations without the improvement in the aerosol wet removal scheme tend to overestimate the BC and CSAR concentrations in the atmosphere. A quick summary to wrap up my key findings. Overestimation of convective frozen water content can be partially relieved by improving the convective snow terminal velocity parameterization, and especially by including grapple microphysics. The improved aerosol wet removal schemes reduce the overestimation of upper tropospheric BC and CSR concentrations by a factor of 10 and 1,000, which is very promising. In the bottom, two recent publications are attached for a detail. For your reference to the details, which I do not have time to walk you through in this talk. And thank you very much for your attention.
Thanks, Lin. Looks like we've come full circle from Pengfei. You seem to match the data as well. Don't know why, but what the time step is, we can talk about. So I'll hand it off to Jinan.
We have a few questions here for discussion, but actually we probably don't have much time. We can continue this after the session on the Slack channel. And but I think there's some also questions for some speakers. I think maybe it's good to have people to have some clarifications. Some people has quick questions, particularly related to how to synergetic work together on the things, all the model data integration approaches. Those things we can discuss some. I can start with one question if nobody start here. So yeah, I think Sue, have a very good point about how to get this model data comparison and particularly integration together with three approaches. Particularly with the radar simulator and the tracking. We can track the updraft sail to have concurrent measurements on the aerosol, Microphysics, thermodynamics. That would be what we are targeting in the trace field campaign. Then Hugh mentioned that in the chat box, he mentioned there's another very good approach, which is piggybacking. Can be used for isolate the macrophysical process, the aerosol impact on through macrophysical process effect. The other one I want to comment is that with the Lunin's work, they have done some simulation with Wolf, and it's very nice to show in that the supersaturation decrease. It's mainly because of the macrophysical effect, the aerosol impact condensation, and then bring down the supersaturation significantly in the polluted condition. And that is a lot because the feedback of the macrophysics to dynamics. So those are one of the examples that can, to connect it with the processes in the model. I would like to open to others for those questions and quick comments. Don't want to take all the time on that.
So let me actually just, since Pengfei and Lin talked about, they seem to match the BC salt data. Can you both resolve, is this still a fundamental time step problem that Pengfei said, or this parameterization that using Ling gets around that? So you're coming to the same results. Can you both comment on that?
For my point of view, it's not so the problem time step is more like default CESM or CAM missing some fundamental mechanism that they don't have secondary activation above the cloud base. I think that's a problem. Lin can comment on that too, please.
I think we approach the very similar problem from a different angle because we now have the cloud microphysics for deep convection. So we can have the detailed cloud microphysics for the aerosol processes now, instead of like using the deterministic convection scheme like the GM 1995. So we have detailed processes for the cloud microphysical processes for the aerosol wet removal processes. That's one our advantage for approaching this problem.
I know a lot of people are in this. I'm a little bit more process guy, so it looks like the models are catching up, and we saw some studies. But maybe since there are a lot of SOA formation, I mean, there is seems to be a theme is there's a lot of scavenging going on in deep convection, wet ones. But there is some SOA formation. Maybe some measurement people, SOA group can pipe in and comment on that. What's the needs there? Manish, John, Joel, anybody?
I could just mention that in the next, another breakout session, I'll be presenting on some LES simulations we've done where we have a cloud, basically a parcel trajectory model that's coupled to high resolution chemistry. We simulate the volatility distribution and scavenging within the cloud. So SOA formation in the cloud so far has been pretty hard to predict happening just because the scavenging of low volatility material that might be produced in the cloud is so efficient. And so we don't find a lot of SOA formation in the cloud, but certainly in the outflow, the detrainment areas, that's where we would get SOA formation. I don't know if that directly addresses what you're asking about, but scavenging in the model, at least the way we've described it, which is try to be pretty faithful using solubility estimates and volatility estimates. It's, even though the timescales might be short in some of the updrafts, it's still, there's so much condensate there that the uptake of any semi-soluble or low volatility vapor is pretty efficient in the cases we've looked at.
Yeah, I want to add that that is really upfront area. And Monish has an early career project. It's work on the modern part.
Mm-hmm.
Yeah. So.
Yeah.
Yeah.
Manish,
So,
you want to pipe in?
yeah, I just wanted to mention that in addition to, so obviously there is transport. Deep convection has a strong potential to transport the semi-volatile gases all the way to the upper troposphere. Temperature plays a strong role where it can condense a lot of these vapors. And then in addition, there is a cloud chemistry and aqueous chemistry happening during the transport, which can also form SOA within the cloud droplets as they are being transported up. So I would say that it's a multidisciplinary problem involving both chemistry of SOA formation, deep convective transport of soluble gases and tracers, the temperature, the effects of temperature on their condensation and chemistry, and also the role of how some of these gases also contribute to new particle formation, especially in the upper troposphere. So when you have, for example, monoterpenes, which can be transported, the oxidation products can condense and they can have new particle formation. Actually, over the Amazon work from our group, which Benzao was leading, showed that you can have like up to 100,000 particles per centimeter cube being formed in the upper troposphere. So new particle formation, the effects on mass of SOA, and how it is coupled to the convective transport and temperature and humidity and cloud chemistry is something which is really important, and we are looking at it from all angles. Thank you.
Excellent. So yeah, no, I think this is all consistent. Maybe I'll follow up from Joel. I mean, there are some gases that are not soluble. Does it matter? I mean, have you looked at which gases are emitted and don't dissolve in clouds? And this residence time, how fast is the updraft that Raymond also talked about? There's some dynamics also. Have you looked at that, Joel?
Yeah, the solubility definitely matters. Something like isoprene is not scavenged at all, but something like formaldehyde is mostly scavenged. And then if you get to anything like that is an oxidation product of isoprene, for example, like the first generation hydroxynitrate would be completely scavenged. So we did a whole range of Henry's law constant species and vapor pressures and looked at the efficiency of scavenging within the convective core. But like Manish just mentioned, of course, if the cloud droplets are having chemistry going on inside the cloud droplets, then the cloud droplets then detrain and evaporate. You could have net SOA formation by that process if they hadn't precipitated. So, and that is not something that we have in our parcel model now, but we could certainly add it. We were doing simply the vapor transport and then chemistry of the vapors into aerosol formation.
So maybe we can have your detailed discussion in the Slack channel about the details. But I would like to get back to how we can work together, like on those group. I feel we like Raymond presented also the chamber work about this high supersaturation awake, which will impact condensation, and then the other processes to impact the ramming and then grapple. Those are very good lab measurements, which I hope we can work together on the tracer. In the tracer field campaign, we will have this tracer modeling group, which organized by me and by Sue and me. We will have this model intercomparison, continued model intercomparison, also with different ways, such as constraint dynamics. Just look at the microphysics, like a piggyback can do, and but a piggyback indeed they cannot assess anything about the feedback to the dynamics. So, but that's good to isolate the microphysics impact. So this is something we are considering, and the chamber data can naturally work together to look at this microphysical processes. So Raymond, I would encourage you to participate in the modeling group, tracer modeling group, and contact me if you don't know how to participate in that, so that we can definitely work together on the things about how aerosol would impact those processes. Another thing I want to mention is the global model.
Yeah,
sorry.
maybe I have a question for both. I mean, I just don't want to be, I want to have model measurements. So Raymond and Jinan, and maybe any tracer person, beyond the lab, other ways of detecting these things in the atmosphere, or these cannot be resolved? Can you somehow monitor humidity in the wake, in situ or other ways? Can that be done?
Yeah, so this is Raymond. I would say, the easiest way to find signatures of this in the atmosphere are indirect. So, for example, strong bimodality of the size distribution would be one indicator. And there are other ideas that we have. And Jinan is right. I think it's great to have a focus on this, amongst the other topics for the tracer/escape campaign coming up. And definitely we'll have the holodeck flying for the escape campaign. That's the NSF side of tracer. And so we will be definitely looking for microphysical signatures. I don't have much hope that we would be able to measure relative humidity in these wakes. I mean, we can't measure supersaturation as it is even in the bulk cloud. But, indirect signatures, I think, are real.
Yeah, if we can measure supersaturation, that solves a lot of problems.
Well, I'll give you a crazy idea. I'm sure I'll get hammered for it, but the big signal is in not RH, but isotope del D. So if you can somehow, not for this campaign, I think deuterium will give you some measure of that. And people are flying such instruments.
Okay, yeah, so maybe in the end we can get to the global model. It's very nice. Guang presented, this, put this microphysics into cumulus parameterization. Usually those parameterization doesn't consider convective microphysics, but this is a big step, put in there and showing that with constrained dynamics, thermodynamics, we see aerosol impact is significant, but with the large scale adjustment, the aerosol impact is a little bit, it gets smaller. And I have a comment on that actually, Guang. The two-moment microphysics which you are using for global model does not consider supersaturation, which is a saturation adjustment approach. That's actually prevent from the warm phase, water phase invigoration occurring. So that impact actually in the tropics, because of the humid condition, it could be the dominant aerosol impact, which was excluded still. But we don't have a solution right now for the global model because it's so difficult to parameterize this subgrade supersaturation. So I think with high resolution, this is our last question. With high resolution E3SM, we can maybe do this and to look at the large scale feedback. This is something we will not be able to do much because with the limited area model, it's only a focus or a limited area. So that is something we move forward. It's very hopeful for this community to look at those effects and to understand how aerosol will impact the convection precipitation globally.
Yeah, do you want to just respond to your comment? Yeah, you made a very good point. And as a GCM model, we are facing some difficulties in the sense that, as shown earlier today by Sue, that within the CRM community, there's still a large uncertainty in the simulation of aerosol effects. And in our case, we're trying to learn from these high resolution simulations. And we can only represent some of these that we can represent. For supersaturation, for instance, it's going to be harder before we learn anything from you guys in terms of how they can be represented in terms of bulk properties.
Hey, Jinan, we're almost done. Let me just throw, there's a Slack channel that's up there, so please communicate. The other just quick questions for Sue and Bill is, and for the Scream and Eagles, is there any coordination amongst all these modeling activities so we can sort of connect them in some manner? Maybe Sue and Bill, I mean, is LASSO going to be available for Tracer?
Yeah, so well, sorry, Bill.
No, go ahead, that's fine.
Okay, so yeah, Dubey, for the modeling activities, as Jinan mentioned a little bit, she and I are overseeing a lot of the modeling activities that are in association with Tracer, right? So those are Tracer specific modeling activities where we're trying to bring all the models together as well as observationalists to really tackle the problem that I spoke about first today. So that's, that's an organized effect under the ASR banner, and we welcome anybody. I know Jinan and I are more than happy to have everybody on board, observationists, modelers, whatever your interests are, we're very welcoming to anybody who wants to be involved. And then there's also been some activities under the ACPC banner that Jinan and Mike and Scott Collis have all been involved in. So there is some organizational oversight there, but I think probably the big one, Dubey, is this one that Jinan and I are leading in association with Tracer. And if you want to join that and you want to be a part of that, just email Jinan or me and we can easily point you in the right direction.
That's excellent. So no, that's what I wanted to reaffirm. And the last question I had, Sue, and Bill, you had something to say? I don't want to interrupt you.
Oh, we haven't talked about LASSO in the context of tracer yet. We're learning a lot from the approach for cacti that probably could translate into tracer and allow us to spin that up faster. But it would depend on priorities of the ARM program in terms of.
And I'm sure you can connect with Sue and Joan, so that's good. Just even before. And the last question I had, because Christine gave a talk and people were using auto-conversion parameterizations. So I do know machine learning is an important topic and it gets attention. So we're getting a lot of data. So keep also thinking about how machine learning, which I think Christine had a very good talk yesterday, where she actually used it to develop a new auto-conversion parameterization. I don't know if that's even being used in GCMs yet. Maybe some GCM folks can comment on that.
So Dubey, we have this EAGLES project. We're developing the machine learning based droplet activation and also auto conversion. We have tested in E3SM.
Great. So I think you're covering that. That's good. So you can have the last word, maybe to follow up on Slack, and also what elements we can be stressing and mechanism for an overview paper. Maybe I'll hand it off to you now.
Yes, well, a couple of minutes over the time. Thank you very much for attending the session, and for particularly thank the presenters for the nice presentations. And I will post these questions for discussion on the Slack channel. And really we are considering overview paper, particularly in terms of how to set up this modeling data framework to work together between the modelers and the observations. Also bring people from different areas like aerosol, chemistry aerosol, and the cloud convection precipitation. This is something I think it's very useful, and particularly under the context of the trace and field campaign. So we really welcome the further discussions. Again, thank you. Have a good day.